Hello everyone. I hope everyone is able to hear my voice. So, I start with my background. So I'm a technical partner at Developers Mania, for those who don't know me, and for those who have worked with me. I have 6 years experience in programming, and I'm passionate about building technology that drives impact, leading teams that create solutions shaping the future. So today we are going to talk about the need for architecture. So that will be our topic. And I want you to participate with me as I give this talk. Who has ever joined a project where you have seen the architecture of the code is spaghetti? Or you guys don't code? So if you ever programmed or joined a project, then you see that the code base is messy, the architecture is not there. Okay, who here in a project has made the architecture messy? Anyone? So today I'm going to not give you the right architecture, but I'm going to try to change the way you think about what architecture even is, because most of us have it wrong. We will start with definitions. Then we are going to see how it works and everything. But before we go to definitions, I start with the historical context. So by context, I don't mean when I start context, I say let's start at the beginning, where software started, the industry, not the project, the industry. So here is a picture of the first programmers. As you can see, they are not writing software. They are literally putting buttons to a machine. So they are literally programming. That was the first computers, the ENIAC, the world's first digital computer. And as the picture shows, this was the first programmers. They are mainly women, 6 primary programmers. Yeah, and the nature of software has evolved since then. So this was the part of the software. At the beginning, software was part of the hardware. Software and hardware were not distinct, they are the same. As you can see, software, those are the programmers and that's the computer. There is no writing software. It was the same. Then the second revolution came when they started writing bespoke software for the machines. So what I mean by this is that, for instance, somebody creates a computer system or a digital system. But for it to run, it needed software. But because there was no software industry at that time, every software was bespoke for that system. So like for instance, writing, I know most of you have used a TV remote. See, it also has a software, but that software is bespoke to that remote. And you cannot also use that remote to control other things, so it's very bespoke. So that's what I mean by bespoke software in the machines. And the biggest issue at the time was decoupling the software from the hardware. So the first was software and hardware at the same time. The same were coupled. They are the same part. Then they were separated but still coupled. Then the third revolution ushered a new golden age for software, where software and hardware was decoupled. And software at that time was written for two things: one, mathematical and scientific, and two, automation of business processes. So this is a time that we saw the beginning of programming languages like COBOL and Fortran, and most of the systems were IBM, insurance, defense, taxes. So the software which were written were to automate the business's processes. In the earliest days of computing, the most expensive thing in the room was not the developer, it was the machine. CPU time, cost, real money, memory was measured in kilobytes. So at that time, machines were big, but the computation was very low. Like for instance, your phone at the moment has more computational power than all the computers at that time. So that's how much we have advanced in terms of technology. And these were the constraints that the developers were facing at that time. And this is where structured programming was born. People like Gistra argued about go-to statements, about what go-to statement was harmful, not because it was technically wrong, but because it made programs impossible to reason about. And this is the first architectural argument in software history. The argument was that the shape of your code affects the ability to think about it. So the way your code was shaped is influenced the way you thought about it. And that's how software architecture started to be introduced. Then by the 1990s, architecture gets its name and started being a mainstream thing. And the reason was that system had grown large enough that a new role started emerging. People didn't just write code, but thought about how code should be organized across a whole system. This is when software architecture became a real title. So 1990s, it was just before the internet. Before the internet came to being, and as you can see here, there were still systems like Microsoft Word, Microsoft Windows systems. So you can imagine you've been tasked by writing the Microsoft Office. So how do you architecture it so that it can work in Apple MacBooks, in PC, on all types of OS? So this is where the architecture started coming to be. Then the last evolution was the internet breaks everything. So with the breakout of internet, the systems evolved from single machine to now handling many users. And it was not thousands of users. For instance, a single PC like this one can be used by only one person, even your phone by one person. But the apps that are in your mobile app can be used by billions of people. Like WhatsApp has billions of users. So how do you architecture a system that can sustain that many number of people? And that's where architecture is very important. So Grady Butch, the co-creator of UML, I know most of you have interacted with it. The entire history of software engineering is one of rising levels of abstraction. So this is when architecture stopped being a document you wrote once and became continuous conversation. During the internet, everything started to change and evolve. There came the introduction of Agile, where you stopped planning so far ahead. Like before, Agile was waterfall, where you planned, then you wrote design documents, then you started implementing, then you tested, then you deployed. But with Agile, everything changed. You stopped planning so far ahead. Then DevOps arrived, deployment is part of the design, cloud arrived, infrastructure is just another API. By the 2010s, frameworks and cloud providers had absorbed so many architectural decisions that the modern developer inherits them without realizing it. So, I want to get back to this quote about the entire history of software engineering is one of rising levels of abstraction. By this statement, what Grady meant was that the tools that you use, they are so much abstracted to a point that you don't do architecture. Has anyone ever done real architecture when writing any software? Or you just use Django and Vue and all the other tools like Next.js, React. So when you use a framework like Next.js, the architecture is there, but it has been abstracted. So you don't do the architecture yourself, but many decisions have been made. For instance, when you use the Next.js, you have already used React. When you use React, you have already used JavaScript. So, and when you use Next.js, you also are somehow required to use Vercel. So your architecture is already defined and abstracted. When you use something like Django, it's very abstracted to a point that you know what you don't know what the architecture is. Another example is Laravel. If you have used Laravel, you know that Laravel enforces the MVC architecture. Yeah, so it forces you to use that architecture. But it's not that it forces you, it has just abstracted that level of you choosing between microservices, MVC, and all the others. So let's now enter to software architecture. So what does software architecture mean? And in simple terms, all architecture is design, but not all design is architecture. Architecture is a significant decision, significant measured by one thing. So how do you know that something is architecture and another is design or implementation? What is the difference? Only one thing, the cost of change. So if you have ever programmed a system or build an app or anything, you can change a lot of things, the code, the design, the everything, but there's one thing you cannot change, the architecture. And by architecture I mean, can you change the programming language mid-project? You can't, right? And the reason is because it's costly. So by that definition, you choosing a software programming language is an architectural decision. So that's what it means by software architecture. Anything that you cannot change after you have started doing your project is the architectural decision. So the higher the cost of change, the more architectural the decision. Architecture isn't a layer of your system, it's a property of a certain decision. The question is, what makes a decision architectural? One thing, the cost of change. If you could write it in an afternoon, it's not architecture. If somebody told you, maybe a client or your engineering manager told you to change one specific theme by tomorrow, then that's not architecture. If changing it requires 3 months, 4 teams, and a prayer, then that is architecture. For instance, which I'm going to show in the next slide, a good example is something like a database. Can you change the database mid-project? No, you can't, because some databases are non-relational, others are relational database. So if you change everything. For another way is if you change the API, how the API has been configured. If you are using REST API, then then mid-level you cannot change to GraphQL or to another API. So that is what architecture is. Ralph Johnson sharpened it by saying architecture is the decisions that are hard to change, not the most visible, not the most impressive, the ones that once made shape everything else. So a simple thing like deciding to build a mobile application using Flutter, it's not it's a very important decision, because if you say you are using Flutter, you are going to have issues to deal with. If you use Expo or React Native, there are other things they are going to face. But if you decide to use native like Android or Swift, there are also challenges that you're going to face. So that is what architecture is in simple terms. Then let's do a little exercise. So switching your button color, for instance, for those who do UI programming like front end or mobile, switching your button color is design. Switching ORM is probably architectural. I've ever tried to change an ORM mid-level, and it's very hectical. So it's probably architectural because it changes everything. Switching a message queue, definitely architectural. What about switching your cloud provider? Has anyone ever deployed a program? I see how it's very costly to move from one cloud provider to another. It changes everything, even the costs and all the other things. It changes everything. So the cost of changing something mid-level is what determines what architectural it is. So, but if that is that is architecture, what is not architecture? Architecture is not a diagram. Most people, when most people think that architecture is diagram, like for instance, go and search the architecture of Netflix. You can go and search even right now, and you will see diagrams and very beautiful done GIFs and to tell you about the architecture. But that's not the architecture. Architecture is not a face. You don't do architecture and then start coding. Most of us have very rigid way of doing software. You start by writing SRS, then you do architecture, then you do design documents, then you start programming. There's nothing wrong with it, but architecture is not a phase that you can start now, then you stop. Once the project starts, the architecture decisions start from there. Then over time, you're going to change and adapt to it. It's not only for big systems. Even a script that 3 people depend on has architecture. It has just very little of it. However, try to delete a function, then it affects the whole thing. So even that small thing is architectural because it affects a lot of things. Somebody said, Grady Butch still said, the code is the truth, but it's not the whole truth. So code tells you what the system does. For instance, I can take your source code, maybe it's a to-do app, and read the source code, and it will tell me what the system does, but it doesn't tell you why decisions were made. So for instance, if you decide to do, let's say, a good example, an event ticketing system, where you buy tickets like Luna, a system as simple as that. Why did they decide to use Vue and not React? So those things you cannot know by reading the code. So code tells you what the system does, but it doesn't tell you why the decisions were made. So you don't know why the engineers used Vue or React or Angular. What constraints existed. So you don't know what they were dealing with when they were building the system. So if they didn't have enough money for cloud, for expensive cloud, that's why they use a certain architecture. So you don't know, and the code will not tell you what the team was afraid of. By looking at the code, you cannot know what the team was afraid of. That invisible layer, the rationale, is part of architecture too, and it's part we lose most often. So most of us rush in to write code, but we don't know the decisions and the rationale of using Vue, not React, not using Django or anything. You don't know. And if you lose that, you also lose the architecture. So why does it matter? Somebody says there is great, but nothing makes an idea stick like watching someone else pay for it. So I'm going to show you when architecture costs greatly. So I start with a very expensive mistake that was done by NASA. So NASA lost $327 million US. How much is it in Kenyan shillings? 326 million. Maybe billions. Maybe a whole county government expenditure for a whole year. So they lost that for one mistake. Somebody chose metric system, the other one chose the imperial system. By metric and imperial, I mean somebody used kilometers, the other one used miles. So a simple decision like that one, using miles or kilometers, it cost 327 million. It was lost. The satellite was lost after launch. So you can imagine you are the programmer who did that. What will you do? So has anyone ever experienced something like that? Maybe you have used a 24-hour system of clock other than the other one. Or another example, which other example I know of that maybe you have ever encountered? Maybe you have used dollars instead of Kenyan shillings on a system, and that change can affect a lot of things. Maybe you have put US dollars to test your system, then you say the system you have programmed, it will take only 100 Kenyan shillings, but in your programming you wrote 100 USD. When you go and test, $100 has gone. So those are the things that architecture will cost you. Another one, which is not costly but a good thing, is the AWS. This actually is a success story. So with AWS, how it started, Jeff Bezos used to write memos, and in this memo around 2002, Jeff Bezos sent an internal memo. It had 3 rules. All teams must expose their data and functionality through service interfaces. Then teams must communicate only through those interfaces. Anyone who doesn't do this will be fired, and no exceptions. So this was a very infamous memo at that time, but because of this, it affected how Amazon was run, and it also brought along the creation of AWS, because what they did by doing this, they used a concept called dog fooding. Dog fooding is when you eat your own dog food. But what that means is that you write the code that you use. For instance, if you write a code that does project management, then you use it, that is dog fooding. So when you take it to the market, you already know because you are the user. So AWS, which now runs a significant portion of the internet, was not a product strategy. It was a side effect of good architecture discipline. The product came later, the architecture came first. So Conway's law ties it together. Organizations design systems that mirror their communication structure. So the law says that organizations design systems that mirror their communication structure. So the way you communicate among the developers is how you design the system. It doesn't matter how good you are at architecture. If you don't communicate, then it will all fall apart. And over the slides, I will show you. I will tell you about how misalignment costs everything. You can when architecture and coding misaligns, everything breaks. So at the beginning, I showed you. I don't remember which slide, but at the beginning I showed you about you. I asked you if you have ever joined a project when the code is not that much well designed. So most people call it legacy code, but legacy code is not bad. But it's not a bad code written by bad developers. It's code that outlive the context it was written in. So the moment you write a line of code, it becomes a legacy system. So the moment you write anything, even that login system, it becomes legacy, so that somebody else will come to maintain it. So legacy code is not that code that has stayed for 50 years or 10 years, or a system like Java written code. No, it's legacy code is code that is written. So why do we sometimes complain about legacy code, or saying like that code was bad, this code was written badly? It's not because that it was badly written or had bad developers, but because the context changed. The context of by which the software was written changed. The team changed, the business changed, the infrastructure changed, everything changed. For instance, if you take the Microsoft Word that was written in 1990 and the Microsoft Word that is now you can use online, is it the same? It's not the same, because the people who wrote it changed, the business changed, the infrastructure changed. So that's why some code may look outdated. But the code is still there, faithfully doing what it was told to do in a world that no longer exists. So if this is true, but why do migrations fail? Why is it hard for somebody to migrate from a legacy code to a new, more efficient code? Because information is lost over time. The original developers leave, they cash out, and with them goes the rationale. So for instance, if somebody starts I've inherited a lot of programs of software, and one of the things that once you do it for 2 months, you realize that you need to restart the whole thing because you don't understand the architecture. So that's something that I've witnessed myself, working on inherited code. But it's not because that the software was written badly or it was not doing. It's because there was no architecture that I could learn from. So when you say that the architecture is a bit of a mess, it's true, because the programmer who wrote it had a different constraints, different requirements, different everything. When I inherit it, the context changes. So that's why when you inherit a code, it becomes messy. So let's go to the big ideas. So this word cloud, when you see it, it has concerns. By concerns I mean things like communication, complexity, schedule, reusability, maintainability, usage. These are the concerns that architectures face. And apart from concerns, the other thing that influences architectural design is stakeholders. So I want to participate, all of us to participate. How many stakeholders do you know? For instance, a software you have programmed. How many stakeholders do you know? You can shout the answer. Stakeholders involved in a software project. Huh? Yeah, customers. Yeah, clients, that's one. Which other stakeholders do you know of? Huh? Developers. Yeah, developers. Which other stakeholders do you... So there are customers, which are part of the business, the people you're building software for. Then the users, the people who use the software. The developers who develop it. And for instance, if you work in a company, the business people who decide how the business is going to focus on. So those are the stakeholders. And if you continue the other stakeholders, like the people who are going to maintain, the people who are going to secure the system, the cyber security people. So those are the stakeholders of the project, and the stakeholders decide what the architecture will be. So concerns encompass a broad range of issues possibly pertaining to any influence on a system in its environment, including environmental development, technological, business, operations, organization, political, economical, legal, regulation, ecological, and social influences. For instance, I'm going to give you something that affected me recently. So we had a software program that we had programmed, then the database was stored in MongoDB servers. And the MongoDB servers were in Bahrain. So the geopolitical issue in Iran affected our code. That all the data that we had collected over 2 years, all of it was lost. So the whole software was affected. So issues like geopolitics may seem not a big issue in writing code, but it will affect you later. Imagine if it was a living software. Maybe it was a software about M-Pesa. Maybe M-Pesa was hosted in Bahrain, and then the servers were bombed. You see, issues like this one, it might not seem trivial at the moment when you write code, but they will affect everything. So that's why I'm saying the cost is what determines the architecture. So the best architecture decision is often not yet. So because of this, the cost of the decisions that we make, we should be very careful when we make the decisions. By this I mean that every decision that you make, if you can delay it as much as possible. So Martin Fowler said big designs up front, mostly a trap. Like when you design something big up front, it's a trap. The idea that you can design a system completely before it assumes you know all the requirements, all the constraints, and all the ways the world will surprise you. You don't. Nobody does. So like for instance, that issue about the geopolitical issue in Iran affected our code base. So we could not know that, but because we have known that issue now, we'll be very careful next time so that we can use a different architecture, we can store data elsewhere. So those are the things that you don't know. Nobody does. So if you make that decision and stick with it at the beginning of the project, it will affect you. So the alternative is not design, it's preserving optionality. Make reversible decisions reversible. Make irreversible decision deliberately, late, and with full awareness that you are closing a door. For instance, if you decide to do a monolith, you decide to use C# to do everything, backend, frontend, mobile, everything you do with C#. Then a bug which has been discovered in the C# program. So it will affect everything in your software. But if you choose different programming languages so that you can mitigate the issue of the code being affected in the whole system, or maybe writing a different code base for front end and back end. Some people mix it the same, they couple it together, but if you can have the wisdom to separate it so that you can maybe decide I will use React, then I will change to Angular later on. So those are the things that I'm talking about. You make reversible decisions. There's this concept of evolution architecture that takes this further. Instead of designing the perfect system, define fitness functions, measurable properties your system must maintain. So architecture, with this evolution architecture starts being a blueprint. In the world outside of software, architectures write blueprints, right? So also in software, we write blueprints. The architects write blueprints, but we have evolved from that. We don't write blueprints at the beginning, like you draw once, then everything follows that. It becomes a set of constraints you enforce forever. So it also helps, like when you are a small team of developers and you don't have the capacity to employ an architect or somebody who is going to focus on architecture. You can also use this to guide you. You don't make decisions that will be like there until the end of the project, and it will affect everything. So when you go back to these issues like I don't know how to pronounce that, but what that means that your system can work with other systems. Like for instance, can your API work with, for instance, you are creating a fintech app. Can your API work with other APIs? Like can it be integrated to the global finance? If it cannot, then you have not looked at the concerns. Issues like affordability. For instance, if you write you architect something, then it's going to cost you more than the revenue of the software that it's bringing. Then you have not looked at the affordability. The regulations. For instance, Kenya has different regulations to the US and the Europe. Most of the time, even when you apply for jobs in Europe, they tell you, do you know this, what is it called, the European Union something for data. So it affects everything. Even the AI in Europe is different from the AI in US. So everything changes according to the context. So what does it mean now that we have agents writing codes like Cloud Code, Codex? What other agentic tools do we use to program? So if you're using these things, then how do you solve the issue of architecture? So context is architecture. So when agentic coding tools started handling real code bases, people noticed something. They kept doing technical, correct things that were architectural wrong for the specific project. Don't know if you have ever told maybe Gemini or Cloud Code to generate a specific thing you are struggling with. Then when you try to integrate it to the thing, it's not doing the same thing. For instance, when you tell it to solve an issue you're doing with login system, then when you try to enter it to the code base, it's not matching with the architecture of the API or the other things. So context is the architecture. So the teams doing this well are investing in making their code base legible to an agent. So when you write the code, you make it so that the agent can know what you are doing. Clear modules, boundaries, explicit decision records, documented rationale, architectural decision records. So the ADR, I think you're going to use in the practical session. you're going to write a few ADRs. Are sudden not just good documentary practice, they are training data for your AI collaborator. So the habits that make code bases maintainable by humans, naming things well, keeping modules small, documenting the why, are exactly the habits that make the code bases navigatable by agents. So architecture is a social activity dressed in technical clothing. So if you have noticed, the whole session, I've not talked about the technical things about the UML or the other design, the patterns, the other things, the architecture. You're going to read more if you're interested in joining the architecture. But architecture is a social activity dressed in a technical clothing. So the thread through everything we've covered, from memory pools in 1950 to agents today, architecture has never been primarily a technical problem. So from the start, like the issue with the telescope that was lost, it was not a technical issue, it was a human problem. Like one programmer wrote in miles, the other one wrote in kilometers. Then that, when it was released, it got lost. So that was not a technical issue. I'm sure any person who writes code for NASA is very well qualified. But the decisions that they made, maybe trying to use a different, miles or kilometers, it affected the whole thing, and 307 million was lost. So issues like those ones, like the issue where we decided to host our whole thing in a server that we didn't know that it would be affected, it affected us. So issues like those are not technical, they were decisions. So the context changed and the code didn't. So we should not take shortcuts when dealing with decisions, with programming decisions, what language to use, what architecture to use, where the cloud to use, because you can host your cloud, you can host your code in AWS or in Vercel, then it affects how everything does, your costs or your maintainability or all the other things. So you don't architect systems, you architect the conditions under which good systems can emerge. When you go back to this quote, the entire history of software engineering is one rising level of abstractions. Right now, with AI, we have reached a new level of abstraction. People are not writing code right now. We are writing specs so that you can guide the code through. We can guide the agents to write the right code for us. So abstractions will continue rising, but the core principles and the core fundamentals of architecture will not change. And the things that they were struggling with at the 1950s and 70s are the same things that we are facing right now. Like for instance, one of the first computers, after this, not this one, after this, it was called time sharing, where they were thinking, how do you share time between computers in the MIT? That same issue, we are going to deal with it, but we are dealing with it with a higher level of abstraction. For instance, how do you share, like for instance, I'm not finding a good example, but you will know how you are going to do it. Okay, for instance, how do you share the same UI, the same application? For instance, you have written a software for managing schools. How does one school has an admin dashboard and the other one has its own admin dashboard? They're sharing the same code base, but how do you do the sharing? So it's almost the same. It's not the same, but it's almost the same architectural problem. So with that, I'm going to leave you with a question, then I will allow you to ask me questions. So what's the most expensive architectural decision your team ever made without realizing it was an architectural decision? So who here has made an architectural design that has messed him or made him regret later? Anyone? Has anyone ever faced an issue like your code base, your data has been blown by Iran? Has anyone ever faced the same thing? So If you have not faced the same thing, then I'm going to stop there and invite Ian.